Okay, this is screencast 5 and force of constraint problem. In this case, I have supposed a string over here which is wrapped around the cylinder, and the string is then held while the cylinder is dropped from that point, and I'll be finding the vertical position of the cylinder as a function of time and the tension in the string as a function of time. So before I start, the generalized coordinates I'll be using are z and theta. Since it is a force of constraint motion, I'll have one generalized coordinate more than what I would need to describe the motion. So in this case, the Lagrangian is t minus u, and since there would be rotational motion as well as linear motion, I'll need this would be 1 by 2 mz dot square would be able to describe the linear kinetic energy, and this would be the rotational kinetic energy, and the potential energy is going to be minus mzz, and this is the Lagrange. The force of constraint in this case is going to be, the equation of constraint in this case is going to be z minus r theta, and now the Lagrangian equation in presence of force of constraint in this one, partial of L with respect to theta plus lambda times partial of F with respect to theta equals to time derivative of partial of L with respect to theta dot. Now solving this Lagrangian equation, what I'll get is lambda equals to minus mr theta dot, double dot, sorry. So now also, now when I solve this equation, now instead of theta with respect to z, then I'm going to get mz plus lambda equals to mz double dot. Now using the value of lambda from this expression over here, I'll be getting z double dot equals to z minus r theta double dot. This is the differential, second order differential equation, and which would be sufficient enough to express all the information, all the motions I need. And here this is the acceleration in z direction, and integrating it with respect to time, I'll get the velocity in z direction, which is equals to zt minus r omega t. This is the velocity of cylinder as a function of time in z direction. And now the tension in the string, which can be found by this expression. The force in downward direction is mz minus tension in upward direction is equals to m acceleration in z direction, and acceleration in z direction is given by z minus r alpha. So az, in place of az, I'll be using z minus r alpha, and then this g cancels away, and then the tension is going to be mass times radius of cylinder times circular acceleration of the cylinder. So that's it.